This interface shows exactly where standard large language models hit a wall. Ask about a recent event, like a Formula One race after 2021, and the model fails because it is constrained by a strict cutoff date in its training data. Retrieval-Augmented Generation, or RAG, solves this problem. Instead of relying purely on static training data, RAG works by flooding the model with real-time internet data alongside your prompt, giving the AI immediate context. Over the next 6 minutes, we are going to build a Next.js chatbot that uses this exact architecture. By injecting specific, targeted data into the prompt, we drastically lower API costs compared to the expensive process of retraining an entire model from scratch. By mastering this specific flow, you create a repeatable blueprint. You can take any private dataset, from company wikis to personal documents, and turn it into a fully conversational AI. Look at this grid. This is how algorithms read text. They convert a word like cat into a matrix of numbers called a vector embedding. Words with similar meanings move closer together on this coordinate plane, allowing the computer to map semantic relationships. Step 1 is setting up our environment. We initialize a new Next.js application and install the required dependencies. For this build, we need LangChain to handle the AI logic, Puppeteer to scrape the web, and the DataStax AstraDB package to manage our vectors. Before writing the logic, we need to adjust our TypeScript compiler options. Open the tsconfig.json file and disable strict mode. Dealing with complex AI response types often triggers immediate type errors, and turning off strict mode prevents those roadblocks while we build. With the underlying theory established and the strict compiler barriers removed, our coding environment is ready to connect to a database. Here in the DataStax AstraDB dashboard, we create a database to store our embeddings. Make sure to select the serverless vector option and pick the closest region to minimize latency. OpenAI's Text Embedding 3 small model outputs 1,536 dimensional vectors. We configure our AstraDB dimension size to match this exactly. Next, we select the dot product similarity metric. It requires normalized vectors, but processes queries 50% faster than cosine, making it superior for real-time retrieval. With the database provisioned, gather your AstraDB endpoint, the application token, and your OpenAI API key. Secure all of them within the project's .env file. That specific combination of dimensions and metric type creates an engine optimized to guarantee high-speed, compatible data retrieval for our language model. Now we supply the data. We create a loading script and define an array of recent URLs, like current Wikipedia pages and Sky Sports articles, to serve as our fresh information sources. To extract that content, we initialize the Puppeteer library. While tools like Cheerio are fine for static HTML, Puppeteer runs a true headless browser, allowing us to load and read dynamic JavaScript elements on those pages. This visual represents our next critical step. We write a regular expression function that strips out all the HTML tags from our scraped content. We want the underlying text, not the formatting. Passing only raw, clean text to OpenAI prevents us from wasting API tokens on useless code syntax. This keeps the vector embeddings dense and accurate. Even cleaned up, an entire Wikipedia article is too large for an LLM's context window. To solve this, we import LangChain's recursive character text splitter. As shown here, the splitter breaks documents down into manageable 512-character chunks. Crucially, we enforce a 100-character overlap between adjacent chunks to ensure a key sentence isn't accidentally cut in half. We then run our ingestion loop. We iterate through every chunk, calling the OpenAI API to generate a vector embedding. Finally, we insert both that mathematical vector and the raw text chunk directly into AstraDB. Executing this seed script transforms standard web pages into a permanent, highly searchable mathematical database. With the database populated, we move to the front end. We construct a Next.js API route that triggers whenever a user submits a question through the chat interface. When a query comes in, the route immediately converts the user's text into an embedding. It queries AstraDB for that exact vector, instructing the database to return only the top 10 most similar text chunks. Those 10 chunks are bundled into a prompt for GPT-4. We add strict system instructions. The AI must prioritize the provided context to answer the question and only default to general knowledge if the answer is missing. By retrieving and injecting only 10 highly relevant paragraphs, rather than passing an entire website into the prompt, we keep the processing lightweight. That exact architectural decision makes these responses fast and keeps costs low. To verify the build, we ask the chatbot a question its original model cannot know. Who is the newest driver for Ferrari? The bot successfully processes the scraped Stry Sports data from AstraDB and outputs the correct answer, Lewis Hamilton. The RAG architecture has successfully bypassed the model's knowledge cutoff. Because the application logic is fully decoupled from the content, the codebase is entirely flexible. Swap the F1 Wikipedia links in the seed script, and you can point this exact same bot at internal company wikis, private APIs, or personal documentation. You now have the skills to build, deploy, and scale custom generative AI tools. Check the description for the full source code and a grant for free DataStax credits to start building your own application today.